What's the meaning of the colorful patterns on this disc full of semiconductors? Find out next on Factory Made. A semiconductor does exactly what the name says it does. It carries or conducts electricity in a very controlled way. Semiconductors are so small, they can't be made individually. So instead, they're made on a disc like this that can hold up to 90,000 of them. Once broken apart from the disc, a single semiconductor isn't even the size of a penny. But without them, you couldn't use a computer, a cell phone, a GPS, or even use the remote to turn on your TV to watch this show. Semiconductors get their start on silver discs, or wafers as they're called, that are made of pure silicon. Silicon in its raw form is one of the most abundant elements on Earth. But rather than mine it, silicon crystals like this one can be grown in a lab and then sliced into wafers. It's perfect for semiconductors because you can easily control how much or how little electricity silicon conducts by deliberately contaminating it with other things later in the process. But because of that, the wafers have to be kept super clean. Just a single speck of dust or the wrong kind of contamination could ruin the silicon. So a robot unpacks the wafers in a sterile, dust-free room and scans the ID number that's printed on each wafer so it can always be traced. Then, the robot stacks the wafers in batches of 25 inside airtight pods. What happens next is a lot like developing film. Only instead of developing a photograph when the film is exposed to light, you develop a roadmap on the wafers for the copper circuits that will carry the electric currents through the semiconductors. To lay the foundation for the circuits, a robotic arm grabs one wafer out of the pod and places it on a platform that spins it, while a nozzle sprays on a liquid photoresist film that leaves an image on the wafer when it's exposed to ultraviolet light. That's why the work has to be done in a room with yellow lighting. Regular lighting contains some UV light and would start to expose the film too soon. The liquid film on the wafer is exposed inside a special machine that shines an invisible UV light on the wafer through a mask. The mask shields most of the wafer from the light, leaving exposed only the pathways that will carry the currents. After the wafers are exposed, they're rinsed with water to wash away the unexposed film around the pathways. Then, a nozzle sprays developing fluid over the remaining film, and instantly the pattern for the electric pathways appears on the wafer. Here's a look at it again. That's the roadmap that tells the electric currents where to go in the semiconductor. But the map itself can't conduct electricity. So the wafers rotate through a chamber where an invisible ionized gas called plasma creates high-energy microwaves that etch microscopic trenches into the pathways. The trenches are later filled with copper, which is an excellent conductor of electricity. But before the copper goes in, the wafers pass through a machine that adds a carefully selected contaminant, such as arsenic or phosphorus, to the silicon. It's called doping, and it changes the number of electrons in the silicon. And by controlling the electrons, you can control the way electricity moves through a semiconductor and from one semiconductor in a device to the next. After the wafers are doped, the copper, which actually carries the electrical currents, finally layers on over the entire wafer and gets buffed down in a machine, so it's left only in the trenches that were etched along the pathways. And that completes a circuit. To protect the circuit, the wafers are heat-treated inside a furnace. The heat causes non-conductive chemicals called oxides to form on the wafers to insulate the copper pathways. And now, for the truly amazing part. The entire process repeats as many as 42 times to layer more and more circuits onto the semiconductor, each with the insulating barrier in between. After the final layer is finished and the copper is laid along the pathways, the wafer spins under a bright light, so a technician can spot check it for flaws. Then, the technician takes a closer look under a microscope that's powerful enough to read each of the thousands of semiconductors on the wafer and their pathways. If everything checks out, the wafers ship out to factories all over the world. And to protect the circuits, the wafers aren't broken apart into individual semiconductors until they're needed to power an electronic device. Anything from a cell phone to a satellite.